As the Pocketer and the majority of HPC systems do not have a desktop environment available, users must log in to the cluster using the SSH program, short for Secure Shell, via the terminal. After providing SSH with a remote host to connect to, for example the login address for a Pocketer, and your user credentials provided by the RTS research team, you will obtain a session on the cluster, ready to run your code and perform your research. When you have successfully connected to a Pocketer, the prompt should change to show that you are connected to the front-end node. Check your QMUL email address for your Pocketer credentials and some useful links to our documentation pages. It's important to note that although your Pocketer username will be the same as your QMUL username, the password is likely different. For added security, some HPC systems require a second layer of authentication, for example using an SSH key pair, which consists of both a private key that is stored on the user's local machine and a public key that is stored on the remote server. If a private key is included in an SSH connection and a valid public key is stored on the remote server, together they will successfully authenticate. Please see the SSH tutorial blog page linked to this slide for more information on how to create an SSH key pair and log into a Pocketer using your private key. We have installed several applications on a Pocketer, including but not limited to R, SAMtools, MATLAB and software compilers, each which are available as modules. To view a list of every available module, run module avail. A few benefits of using modules include the ability for multiple versions of a single application to be installed. Users can dynamically import applications when required. Application dependencies and conflicts are automatically resolved, and additional variables and settings can be automatically set. Loading a module will set the relevant environment settings in your session, for example binary and library locations, so you can use the relevant application on the cluster without any additional installation or configuration required. Loaded applications are only stored in the local session, or the node that you ran module load on. To use applications in HPC jobs, which we'll discuss in the next few slides, you will need to load the module inside the job, because the submission and runtime environments are different. Finally, please do not attempt to install software using yum or apt install, because root or administrator access is required, and installations performed via this method would lose all of the user-friendly benefits that a module provides, and it would not be available across all the nodes on the cluster. To request an application which is not installed, please complete our application request form, which is linked to this slide. Now, let's demonstrate using modules on a Pocketer. Upon login, the environment does not contain any loaded modules, which we can verify by trying to run an application. We should see a command not found error. Before we can use applications, we first need to know which applications have been installed and are available via modules. Running the module avail command will display a full list of installed packages. We can narrow this down by specifying an application name such as R. Here, we only see the versions of R which have been installed. To load a module, run the module load command with an application to import into the environment. If a version number is not specified with an application name, the default version, which is displayed in the module avail output, is loaded. Dependency modules are also loaded if required. Due to module conflicts, it is not possible to load two versions of the same application. Attempting to do this will display an error message and a hint for how to resolve the issue. In this example, we must first unload the loaded R module before loading the alternate version, using either the module unload command or as a shortcut, try running module switch. To view a list of loaded modules, run module list, and finally, to unload all modules, run module purge to return to a clean environment. To submit a job to the cluster, you need to request a specific number of cores, amount of memory, and a runtime. If not specified, each job will default to submit with 1 core, 1 GB of memory, and 1 hour runtime. Once submitted, the job scheduler will add the job to a queue, which will contain jobs from all Apocalypse users. When the requested resources become available and you are near the front of the queue, your job will start to run on an eligible node which has been selected by the scheduler. From a user perspective, you should not need to know which node the job will run on, unless you request specific resources such as GPUs or large amounts of RAM. There are 2 main types of jobs which may be submitted on Apocalypse. The majority of jobs are submitted via the queue subcommand, which will submit a job to the queue, which will start running when resources are available. Once submitted, you do not need to be logged in, and the job may start executing at any time, even out of office hours. The other type of job is an interactive job, submitted with the queue login command, which will request a session on a compute node so you can run applications directly via the terminal on a node. Whilst queue login is useful for quick debugging and job validation, we recommend writing a job script, which we will expand on in the next slide, containing a list of commands to run and submit this script using the queue sub method. You may also request an email when your job begins, ends, or results in an error, so you know when to check your job output. Here is an example of a job script. Typically, you might use a text editor on the cluster to prepare this rather than copying text files from your local machine, mainly for 2 reasons. Number 1, you may experience an issue with the line endings when submitting jobs that have been prepared on Windows. And number 2, working with files directly on Apocalypse provides a much more streamlined workflow to edit and inspect files. At the top of the job script, we have defined how much resources to request for the job. In this case, we're asking for 1 core and 2 GB of memory, which will be dedicated to your job. Note that the HVMem value for memory is per core, so the total requested will be multiplied by the number of cores requested. This often catches users out, and as a result, jobs could be queued for a lot longer than expected because the scheduler needs to reserve more memory for the job. You also need to specify a maximum runtime setting, which if exceeded, your job will be killed by the scheduler. Here we have requested 10 days, or 240 hours, which is the maximum runtime for jobs on Apocalypse. Other HPC clusters may offer a lower maximum runtime. A maximum runtime is enforced to allow other jobs in the queue to eventually run. It also allows us to plan node maintenance, and it encourages good practices in your code, such as scaling to multiple cores or checkpointing. If you have requirements for longer than 10 days, please get in touch with us and we can advise on individual cases. The remaining of this job script contains the actual commands to run on the compute node. In this example, we are first loading the default version of Python into our environment, then running our pre-written Python script which exists in the same directory as the job script. Once the job has been submitted, the Python code will be run. You may also provide some extra optional parameters to your job script, such as combining the output and error files together, providing a job name and enabling mail options. A full list of other options available can be found on our doc site. A direct link to the relevant section has been added to this slide. If you did not instruct the scheduler to join the output and error files together, you will see 2 new files have been created once the job has started running. The first will end with .o job ID, which contains the output that was sent to standard out, for example print statements in Python. The second will end in .e job ID, which contains the errors that were produced during the execution of the job. To demonstrate the job submission process, I have written a small Python script to accept 2 integers, sum them, and print the result. This code is currently being shown in the terminal. Firstly, we can run qlogin whilst connected to the front-end node to obtain a 1-core, 1GB of memory interactive session for 1 hour, so we can quickly test our code. As you can see, our job was scheduled immediately, and we are now running on the compute node. Note the prompt has changed, and you can see a job number has been assigned once submitted. Now let's load the default Python module and test running our code, passing 2 numbers to the script and ensuring the output is correct. We can see the output is as expected and there were no errors printed to the screen. So now we are ready to create a job script and submit using qsub. Type exit to end the interactive job and return to the front-end node. I'm now creating a simple job script which will write the output to the current working directory and request 1 core, 1GB of memory and 1 hour runtime before loading the default Python module and running the Python code. This is identical to the interactive job we ran moments ago. Once the job script has been written, proceed to submit it to the queue using qsub as shown on screen. Once the job completes, if we run ls, we can now see a new file has been created in the same directory as the Python code and job script. This file contains the output produced from the job, which if we view the contents, we can see the same output as the interactive job, meaning the job has completed successfully. There are some utility scripts available on Apocata to check the status of your jobs, the compute nodes, and the queue, which can be useful for you to check how your job is progressing or an idea for when your job will start running. To check the status of your queued or running jobs, run the qstat command without any options or arguments. Jobs in the qw state are currently queued and waiting for resources to become available. Running jobs will have a state of R and will be assigned to a node. The node status command will show the number of free and used cores per node and also how much memory is available, allocated, and the total amount per node, and also a summary at the bottom. You may use switches to display the jobs on a single node or filter by node type. Run node status with the -h switch for more information. The show queue command will print a full list of jobs waiting in the queue from all users. The position shown in the output is relative to the job's position in the queue, meaning that jobs near the top are more likely going to be run next. If you notice your job is coloured in red when running show queue, this means that it's been queued for over 7 days, and you should contact us to check why your job has not yet been processed. To demonstrate checking the status of your queued and running jobs, I have submitted 2 example jobs which we will use for the remainder of this video. By executing qstat, we can see the first job is currently running and the second is being held in the queue. When resources become available, the second will become eligible to run. Running node status will give you a snapshot of the current status of the nodes. Here I am filtering the output to only show the public nodes with the -p switch and the serial nodes with the -t switch. The second job has requested 12 cores, and we can see from scrolling down the node status output that there are no currently available nodes with 12 cores free to accept the job, excluding nodes which are alarming or disabled as they will not accept new jobs. Running show queue will print a list of jobs waiting in the queue. Here we can see the second job is in the top half behind some large jobs, which could mean it will wait in the queue for a while before starting to execute. However, if we view more details about each queuing job by passing the -F flag to show queue, we can see that the majority of jobs above our second job are requesting GPU or parallel nodes, so they can be ignored in this instance, because we submitted a serial non-GPU job. The extra details displayed here can include the parallel environment, memory, GPU or parallel resources, and user quotas. Increasing the number of cores to reduce application running times due to threading is an incorrect assumption. Firstly, requesting more cores may increase the job queuing time, and secondly, not all applications are written to support threading, for example gzip. Before running applications on a Pocketer, we recommend checking the man page, user guide or usage instructions if provided by the developer. If you're unsure, please ask us to check. Finding the optimal performance for an application may take a few attempts, so we recommend running a few short jobs using a variety of core and memory requests to find the best combination for your application. By starting with fewer resources, the jobs will likely be queued for a short period of time or start running immediately. Should an application support multi-threading, you should request more than one core in your job script. If an application assumes each core has multiple threads, you may experience something like this example here. Specifically, looking at the CPU column when running top, you can see each thread is only utilizing about 8% of the CPU, which will significantly increase the execution time. For optimal results, we would expect to see 100% utilization per core requested. If you notice that your jobs are running a lot longer than expected, please get in contact with us and we can check on the status of your running jobs and provide recommendations about optimization. Here is a visual representation of the cores and threading mentioned on the previous slides. In the top example, half of the egg box is full and each egg only occupies one holding slot, which is fine. The second example demonstrates a full egg box with each of the eggs occupying a single slot, which represents full optimization. The final example shows an overloaded egg box, which will decrease performance. Each egg will request time in the holding slot, meaning the CPU will perform a lot of switching to ensure each egg has an equal amount of time in the holding slot. If this analogy was applied to a compute node, each thread will be waiting for a slot to execute its code, and the CPU would keep switching the threads to avoid starvation. This means the overall runtime will be higher and the job will have lower performance. Unlike requesting cores, choosing the right amount of memory for your job can be non-trivial if you do not know in advance how much memory an application requires to run. You may have some indication, for example, if you're reading in a 20 GB file, you'll need to request at least 20 GB of memory. However, it can take a few attempts to find the correct amount of memory to request. Requesting too much memory can cause a job to queue for longer than expected and is a waste of resources. So a good rule of thumb is to start with the minimum requirements and increase memory where necessary. On a Pocketer, jobs are automatically killed if they exceed the memory requested because the job has been allocated dedicated resources from the scheduler, and exceeding these resources could have an impact on other jobs running on the node. Remember that memory settings are per core, so requesting 10 cores with a HVMem value of 10 GB will request 100 GB, not 10. You can see how much memory your job has used by running either the get job ram usage command, as shown on screen, or view the stats website, which will show you a list of your recent jobs. We'll show you an example output from the stats site in a later slide in this presentation. If your job requires a large amount of memory, it can be waiting in the queue for a long time. Therefore, we have some nodes on a Pocketer which are dedicated to run high memory jobs only. If requesting 128 GB or more, we recommend adding the high memory resource to your job script to run on one of these dedicated nodes. Please only use these nodes for legitimate jobs requesting large amounts of memory, because there may be jobs waiting in the queue which do require large amounts of memory, and running jobs may block these from running, which we deem as unfair. requesting a maximum runtime is different to cores and memory because runtime is not consumable per job. If a maximum runtime is exceeded, the job will be automatically killed by the scheduler. So we recommend setting either 1 hour for the short queue described in the next slide, or the maximum available runtime of 10 days. Please note that runtimes cannot be modified after a job has been submitted. When a job has finished executing all of the commands in the job script, it will end, and the resources will become available again for other jobs. Nodes will not idle for the whole requested runtime once all commands have executed. Runtime has a very small impact on the scheduling algorithm and therefore will not increase queuing time. Finally, having a job killed due to runtime after requesting more than 1 hour but less than 10 days is wasteful on resources. We recommend requesting the full 10 days for jobs over 1 hour. For short jobs of up to 1 hour, we have created a high priority short queue to run these jobs with minimal queuing time, which is useful for job script validation, code syntax checking, and resource optimization. The short queue has been enabled on a variety of nodes, including those which have been purchased by other research groups that are not available to all users for jobs longer than 1 hour. An example use case for the short queue is to check that a job starts running correctly, modules have been loaded, the environment set, execution commands are found, and their arguments can be understood, all in a short period of time. If there was an error and you submitted with more than 1 hour, it could be a few hours or days before the job starts running, and it could immediately fail due to a typo or incorrect settings. If you would like to do some quick debugging or testing, run qlogin without any parameters to start an interactive job on the short queue. In the world of Linux, commands will exit with a numerical code, which can be used as an indication of how a command executed. If a command follows good practice, an exit code of 0 means that it ran successfully. However, this does not mean the output will be correct. On Apocrypha, jobs which run successfully will also exit with code 0. Non-zero exit codes indicate there was a problem during execution and the command did not run successfully. Other common exit codes that you may experience on Apocrypha are as follows. Exit code 127 means that a command inside the job script cannot be found or is not executable. To remedy this, ensure that all commands are correct inside the job script and the relevant module or modules have been loaded. Exit code 135 means an application attempted to allocate more memory than was available in the job. The solution here is to request more memory and resubmit your job. A 137 exit code means the job was killed by the scheduler for exceeding either the runtime or memory requested. Please see the memory and runtime slides for more information. You can see an overview of your recent jobs, including the number of cores, memory, and runtime requested, and the job exit code on our stats site. There is a direct link on this slide. Here we are showing an example job details output. Jobs which have exceeded the runtime or memory requested will have the relevant column highlighted in red to make it clear why a job has failed. The final column only displays an exit code for jobs which did not exit with a code 0. In the above example, a few jobs exited with code 137 after exceeding runtime, which is coloured in red. Other jobs have a non-zero exit code and around 50% of them exited successfully with code 0.